Welcome to our comprehensive guide on 3D printing interview questions. Today, we'll explore the fascinating world of additive manufacturing, covering essential concepts that every aspiring manufacturing professional should know. 3D printing has revolutionized how we create objects, from simple prototypes to complex industrial components. Whether you're preparing for your first interview in the manufacturing sector or looking to advance your career, understanding these fundamental concepts will give you the confidence to tackle any 3D printing-related question. Let's dive into the key areas that interviewers focus on most. Additive manufacturing is the technical term for 3D printing. It's a revolutionary manufacturing process that builds objects layer by layer from digital designs. Unlike traditional manufacturing methods that remove material through cutting or drilling, additive manufacturing adds material precisely where needed. The key advantage of this technology is its ability to create complex geometries that would be impossible or extremely expensive to produce using conventional manufacturing techniques. Think of internal channels, hollow structures, or intricate lattice patterns, all achievable through additive manufacturing. This layer-by-layer construction opens up entirely new possibilities in product design and functionality. There are 4 major 3D printing technologies you should know. First is FDM or FFF, which stands for Fused Deposition Modeling or Fused Filament Fabrication. This is the most common type where plastic filament is heated and extruded layer by layer. Second is SLA and SLS stereolithography, uses liquid resin cured by light, while selective laser sintering uses powder materials fused by laser energy. Third is SLM and EBM, selective laser melting and electron beam melting, both used for metal printing in aerospace and medical applications. Finally, polyjet and MJF material jetting and multi-jet fusion, which offer high precision and multiple material capabilities in a single print. Let's examine the FDM process in detail, since it's the most widely used technology. The process starts with filament being heated in the extruder to its melting point. The molten plastic is then deposited layer by layer through a precise nozzle movement. After each layer is completed, the build platform moves down by 1 layer height, typically 0.1 to 0.3 millimeters. For overhanging features, support structures are automatically generated to prevent drooping or collapse during printing. Finally, cooling and solidification occur as each layer bonds with the previous one. Understanding this step-by-step process is crucial because it directly impacts print quality, speed, and the types of geometries you can successfully create. 3D printing materials fall into 2 main categories. Thermoplastics are the most common, including PLA or polylactic acid, which is biodegradable and easy to print with, making it perfect for beginners. A BS or acrylonitrile butadiene styrene offers higher strength and temperature resistance. PETG or polyethylene terephthalate glycol combines ease of printing with chemical resistance. Nylon provides engineering-grade strength for functional parts. Advanced materials open up industrial applications. Metal powders like titanium, aluminum, and steel are used in aerospace and medical implants. Ceramics such as alumina and zirconia offer high-temperature resistance. Carbon fiber composites provide exceptional strength-to-weight ratios, while UV-curable resins enable highly detailed prints with smooth surface finishes. Design for manufacturing, or DFM, is critical for successful 3D printing. 4 key principles guide effective design. First, minimize overhangs and support structures by designing parts that can print without extensive supports, reducing material waste and post-processing time. Second, design appropriate wall thickness. Too thin walls may not print properly, while overly thick walls waste material and increase print time. Third, consider print orientation carefully, as the direction you orient your part affects surface finish, strength, and support requirements. Fourth, account for material shrinkage and thermal effects that can cause warping or dimensional inaccuracy. Here's a simple Python example for checking overhang angles. By calculating the z-component of face normals, we can identify surfaces that exceed the critical 45-degree angle and may require support structures. Support structures are temporary scaffolding used during printing. They're needed for overhangs greater than 45 degrees, bridges longer than 5 millimeters, complex internal cavities, and horizontal holes or slots. There are several types and strategies to consider. Tree supports use less material and are easier to remove, making them ideal for organic shapes. Grid supports provide a strong foundation for large flat overhangs. Soluble supports using materials like PVA or HIPS can be dissolved away, leaving perfect surface finishes on complex geometries. Sometimes, the best strategy is strategic part orientation, rotating your design to minimize or eliminate the need for supports entirely. Understanding when and how to use supports effectively can dramatically improve your print success rate and surface quality. Several critical parameters control print quality and success. Nozzle temperature typically ranges from 180 to 260 degrees Celsius. Depending on the material, PL prints around 200 degrees, while a BS requires around 240 degrees. Bed temperature ranges from 50 to 110 degrees Celsius and prevents warping by maintaining adhesion during cooling. Print speed affects quality and print time, typically ranging from 30 to 100 millimeters per second. Slower speeds generally produce better quality. Layer height determines surface smoothness and print resolution, ranging from 0.1 to 0.3 millimeters. Here's a G-code example showing how these parameters are controlled. M104 sets nozzle temperature, M140 sets bed temperature, and G1 commands control movement speed and extrusion rates. 3D printing has found remarkable applications across major industries. In healthcare, it's revolutionizing patient care through custom prosthetics and implants, surgical planning models that help surgeons practice complex procedures, custom dental devices tailored to individual patients, and cutting-edge bioprinting research for tissue engineering. Aerospace leverages lightweight components that reduce fuel consumption, complex internal channels for cooling systems, rapid prototyping for faster development cycles, and end-use parts production for both commercial and military aircraft. The automotive industry uses 3D printing for tooling and fixtures, custom jigs for assembly lines, spare parts production on demand, and concept validation during the design phase. General manufacturing benefits from production tools, assembly aids that improve worker efficiency, quality control gauges, and low-volume production runs that would be uneconomical with traditional manufacturing. Let's examine 2 frequently asked interview questions. First, what factors affect print quality in FDM technology? The answer includes temperature control for both nozzle and bed, proper layer adhesion achieved through optimal settings, appropriate print speed that balances quality and efficiency, correct retraction settings to prevent stringing, and effective cooling management to prevent warping and improve surface finish. Second, how do you minimize warping in a BS prints? The solution involves using a heated bed at 90 to 110 degrees Celsius, maintaining an enclosed chamber to control ambient temperature, ensuring proper bed adhesion through techniques like using a BS slurry or specialized bed surfaces, and implementing controlled cooling rates to reduce thermal stress during the printing process. 3D printing faces several quality challenges that require systematic solutions. Common issues include layer adhesion problems, where layers don't bond properly, surface finish inconsistencies that affect part appearance, dimensional accuracy issues that prevent proper fit and function, material property variations between printed and bulk material, and extensive post-processing requirements that add time and cost. Best practices to address these challenges include parameter optimization through systematic testing and calibration, material characterization testing to understand how materials behave during printing, process monitoring systems that detect issues in real time, standardized quality protocols that ensure consistent results, and regular calibration procedures to maintain machine accuracy. Implementing these practices transforms 3D printing from an art into a reliable manufacturing process. As we conclude our journey through 3D printing interview preparation, remember these 4 essential takeaways. Master fundamental processes and materials, understanding how different technologies work and which materials to use for specific applications forms the foundation of 3D printing expertise. Understand design constraints and DFM principles. Knowing how to design parts that print successfully saves time, material, and frustration. Focus on quality control and parameter optimization. Consistent, high-quality results come from understanding and controlling the printing process. Stay current with industrial applications. 3D printing is rapidly evolving, and knowing real-world applications demonstrates your industry awareness. With these concepts mastered, you're well prepared for 3D printing interview success. Remember, 3D printing combines technical knowledge with practical problem-solving skills, making it an exciting and rewarding field to pursue.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.